All right, hey guys. It's Tuesday, October 6th, and we're going to continue on, kind of like I mentioned yesterday. We're going to continue moving forward in our graphing unit. To be totally honest with you guys, as far as a unit that we're sort of forced to be separated here and learning and instructing remotely, this is actually not a terrible one to have this happen on. If you kind of remember back, and I know it's been a week now basically since we first introduced these graphs of sine and cosine. One of the things I had you guys do is I said I'm not necessarily going to have you guys or ask you guys to copy a lot of the examples down into your notes, because over time, as you do more and more of these problems, you realize they're very repetitive and pretty simple. But what I would kind of like to ask you guys to do is kind of the same thing today that we did a week ago when I first introduced sine and cosine graphs. And that was just to have kind of the generic like parent graph in your notes, okay? So what I am going to have you guys do today as you're watching this video, if I get going too fast or something, you can pause it. Hopefully you guys all have your earbuds or your earphones, your headphones, and you can kind of be watching this video individually or independently. That way that if you do need to pause this at any time as you're writing some stuff down, you can do that, okay? So just like we did with sine and cosine, I am going to have you add some of this stuff to your notes. All right, so today is the 6th, and what we're going to look at today is we're going to look at tan and cotangent graphs. Okay, and I'm not necessarily that concerned with the examples. I'm going to put some examples on here. We're going to talk about the similarity and the differences between these graphs and the sine and cosine graphs and all that stuff. But ultimately, I would like you to get just a little bit of this stuff in your notebooks for reference. If you hang on to these notebooks next year in college or whatever, and you kind of pull them out to look back at them at some point, you can sort of remember some of the stuff. Or if you find yourself taking kind of a placement test for next year and you want to do a little bit of prep work for that placement test, kind of the same thing. You've got just a generic group of things in your notes notebook that you can look back at, okay? So one thing I am going to ask you guys, and you don't have to write this down, but I'm going to write it down because it's going to help us here. Actually, not even necessarily help us, it's going to be instrumental in our ability to graph these. I'm just going to take a second here and I'm going to redraw very quickly the sine and cosine graphs. So you guys remember we've done this a bunch of times now. If I want to construct just one period of a sine wave, I need the first four increments, because at 0 our graph starts at 0. At 90 degrees we're up at 1, because like I said initially a week ago, if you go to your calculator and you hit sine of 90 and your calculator set to degrees not radians, it'll kick back a 1. And then if you do sine of 180 on your calculator, it'll give you a 0. Sine of 270 on your calculator gives you a value of -1. And then obviously sine of 360 gets you right back to 0. So this is that first period, breaking a lot of lead lately, first period of the sine wave, which we're getting pretty accustomed to, right? So this again, that's the curve, y equals sine theta or sine x, whatever we want to call it, where our x coordinates are degree measures. Okay, compare that now to the cosine graph. Oh, let me draw that a little bit better here just so it looks nice. And if you want, this might not be a terrible thing so that you can look back at it. It might not be a terrible idea for you guys to construct these two curves in your tangent and cotangent graphs, even though we're getting pretty accustomed to it. Same period. It's a full revolution. It's 360 degrees or 2 pi radians, where the key points are 90 degrees, 180, 270, and 360. But the cosine curve, remember, starts up at +1. If you do cosine of 0 on your calculator, it'll kick back a 1. Cosine 90 will give you a 0. Cosine 180 will give you a -1. Cosine 270, 0. And then cosine 360 will give you that. Okay, and then here's the curve itself. All right, there is our cosine curve. Now, what we're going to do today is this, and this is what, again, I would really like you guys to, even if nothing else, by the time we get done taking our notes today, or you guys get done adding to your notes today, it really wouldn't be a bad idea for you to have just the first period of the sine wave copied, the first period of the cosine wave copied, and then we're going to have the first period of the tangent graph copied. But having the sine and the cosine is going to be kind of instrumental, because essentially what I want you guys to remember is this. Tangent, or another way of thinking about, or another way of expressing the tangent curve, is to remember that tangent is essentially just sine over cosine. Okay, so we use this concept, the idea that tangent is equivalent to sine over cosine. We used that when we were working with the unit circle, when we were working with reference angles and all that stuff. But we're going to also use that today to sort of generate our graph. Okay, so it's going to be a little bit of an interesting experiment here, but we're going to do it. And the hardest part is that I'm not there to read your facial expressions or anything like that. It's going to be a little bit trickier for me to just go at this blindly, because I can't see if this is kind of making sense, confusing you, boring you, if anybody's sleeping or anything like that. But we're just going to navigate it, okay? Basically, what I want you guys to think about right now is this. At 0 degrees, okay, and at this point I am going to switch back. Well, maybe I won't. I'm going to stick with degrees right now, okay? So, if we think about 0 degrees, and we want to find the tangent of a 0 degree angle, obviously we could go to our calculator and we could hit tan 0, but we could also just simply think about this. If you have the sine function at 0, okay, the sine's value at 0 is 0, whereas the cosine value at 0 is 1. So if you just put those together, it would basically be sine is 0 over cosine 1. 0 over 1 is okay. 0 divided by 0 is 0. So just like the sine curve starts at 0, so does the tangent curve, but it's because it's sine over cosine. It's 0 over 1. Now, here's where things get a little bit weird. When you move to 90 degrees and you start thinking about the sine curve's value over the cosine's value, well, at 90 degrees, the sine's value is 1 and the cosine's value is 0. So what you get is at 90 degrees, when you plug in 90 degrees for tangent, it's going to give you the same thing that you get when you do sine of 90 degrees over cosine. You get 1 over 0, which does not make sense. You cannot have a denominator of 0, which is why if you go to your calculator and you hit tangent 90, guess what it's going to kick back? It's going to kick back a syntax error, okay? It's going to say domain error or syntax error. What this means is at 90 degrees, the graph does not have a value. That means the graph does not exist at 90 degrees. So what this is going to represent is it's going to represent a vertical asymptote at 90 degrees. Okay? So our cosine graph is not going to be a nice flowing curve. There's going to be breaks in the graph. Well, I shouldn't say breaks. There's going to be spaces in the graph where the function's not defined. What it's going to represent visually is a vertical asymptote. In fact, what I want you guys to see essentially is this. Anywhere that happens, anywhere that the sine graph has a value and the cosine graph has a value of 0, there's going to be one of those errors. It's going to be a sine value over a cosine value, but it's going to be an actual number over 0. So think about the cosine curve. At 90, its value is 0. At 270, its value is 0. At the next 90 after 360, at 450, it's going to have a value of 0. The cosine graph is a value of 0 every 180 degrees. And at those 180 degrees, 90, 270, 450, 90, sine has a value. 270, sine has a value. 450, sine has a value. So what this tells us that actually happens is every spot, 90, 270, 450, and so on, what we actually end up with is a graph that does not have a value. So we end up with vertical asymptotes at every 90 degree increment. 90, 270, 450, and so on. And then likewise back this direction. So I'm going to extend my x-axis back. You might need to, well, you'll want to do it just a little bit too, because the same thing is going to apply at negative 90, negative 270, and so on. There's going to be these vertical asymptotes that exist because, again, at every increment of 90 degrees, you're going to have a cosine value which is equivalent to 0. So you're going to have a cosine value in the denominator of the tangent function that's equal to 0. And obviously we cannot have a fraction with a denominator of 0. What we have to think about then is what happens in the meantime then, okay? What basically or effectively happens is we need to talk about, well, let's see, how do I want to do this? Okay, let's do this. Let's start at 0. We know that at 0, we have this dot at 0. We've already established that. And we know that at 90, our graph does not exist. But let's think about this. Let's think about what's going on in the increment from 0 up to 90. From 0 to 90, our graph is going up for our sine value, meaning this top of this fraction is getting bigger. The graph is going up as we approach, as we go from 0 to 1 on our sine graph, right? We're going up from a 0 value to a 1 value. So you have a fraction here where the graph is getting, or the top half is getting larger. So I'm going to put a little plus sign there, okay, to indicate what's going on in my tangent graph from 0 to 90. From 0 to 90 on my sine graph, which is something I can see that my numerator is getting bigger. My sine value is going up. At the same time, okay, I have, for my cosine from 0 to 90, my value is going down from 1 to 0. So I have a denominator, and maybe a plus sign's not good because that makes us think about positives and negatives. Maybe this is better. My sine value is increasing while my cosine value is decreasing. So that means I have a fraction where the top is getting bigger and the bottom is getting smaller. If you just think about that, what kinds of numbers are rational numbers, meaning fractional numbers, where it's got a larger, an increasingly larger top and an increasing larger denominator? Those numbers are just getting bigger. So basically what this means, as you go from 0 to 90 on your tangent curve, your function value is going to get bigger and bigger and bigger as your numerator gets increasingly bigger and your denominator gets increasingly smaller. So what this creates is it creates a curve that looks like this. We're going to have a curve approaching that asymptote, okay? And the same thing is going to apply basically everywhere or in every one of these increments. If you think about what happens at 180 degrees, at 180 degrees, sine is 0, cosine is -1. So it's 0 over -1, which is 0, right? So we've got that right there. But now, again, we're thinking about this stretch right here from from 180 to 270, okay? What happens is this. I have on my sine value, I have a number that's going to go from 0, and it's going to get bigger and bigger and bigger in terms of a negative. It's going to go from 0 to -1. So my sine's curve is going from 0 closer and closer to -1, okay? And then my cosine curve is going from -1 closer and closer to 0. So what I want, I guess, you guys to see is this. When you're talking about from 180 to 270 degrees, your sine curve is negative, and so is your cosine, because both of these curves from here to here and here to here are negatives. So it's a negative over a negative. And basically what happens is, you're still going from 0 to -1. So your absolute value of this graph is getting bigger because you're going from 0 to -1, whereas the absolute value of this curve is getting smaller because you're going from -1 to 0. It's this same thing. Your top is getting bigger while your bottom is getting smaller, because since both of the values are negative, what do those negatives essentially do to each other? Well, a negative over a negative is a positive. So you end up with, this actually ends up being the exact same fraction. So this curve is doing the same thing. It's doing the same thing from 0 to 90, from 180 to 270, from 360 to 450, okay? Any one of these, the curve is going up. Conversely, if we think about this, and now I kind of got to backtrack these, this you would not necessarily need, well, actually, let's not go left. Let's focus on trying to construct this half of the curve right here. From 180 back to 90, what is the graph doing? Again, 180 back to 90. So if we think about this one more time, what we're really considering is the graph of sine over the graph of cosine. But as we work from 180 back to 90. So from 180 back to 90, the sine graph is going up. So I have an increasing a numerator that's going up. It's increasing, and it's increasing in a positive direction from 180 back to 90. Conversely, on the the cosine graph, from 180 back to 90, I have a graph that's absolute value is getting smaller because it's going from -1 closer to 0. So I have this graph that's getting smaller. So just like up here, this is an increasingly larger number because your numerator is getting bigger while your denominator is getting smaller. The same thing is happening here, but if you think about it, the sine graph from 180 back to 90 is going into the positive direction, whereas the cosine graph from 180 to 90 is below the x-axis. It is a negative number. So what you have here is a positive over a negative, which is a negative, an increasingly large negative number. So what that looks like on a graph is a curve that's getting increasingly smaller, going towards negative infinity. So this is actually what the cosine curve looks like. Or excuse me, the tangent curve looks like. It is an infinite repetition of this S-curve. It's an S-curve that goes, through this center point. It's getting increasingly smaller towards negative infinity to the left and increasingly larger to the right, okay? But it's this exact same curve repeated over and over and over again, okay? So there's a couple different things that I really want us to focus on with this, all right? In terms of what the tangent curve looks like, all right? So again, we have our tangent curve right now over there represented. But when you think about the sine curve, the entire sine curve before you get any kind of repetition takes 360 degrees or 2 pi radians. Same thing for the cosine curve. For the cosine curve to get back to its starting point and start to replicate or duplicate itself takes 360 degrees. When you look at this, each of these two portions of this graph are identical. So in reality, it only takes to go from the starting point to the ending point of a curve before it starts to repeat itself. This right here is only from -90 to +90, and then it just repeats itself. So from -90 degrees to +90 degrees is only 180 degrees, okay? What I guess I want you to see here is this, you guys. This right here, this 180 degree stretch, that represents one period of the tangent curve, where you have to just basically remember the sort of, if we want to call it the starting period, is this one right here. It's the one with 0 degrees, but it goes between -90 degrees and +90 degrees. Okay, if we want to call that our starter, and then everything after that, either to the right or to the left, represents just a second or third or fourth period. Okay, so it's a little bit different from the sine wave and cosine wave in more ways than just simply it's a completely different looking graph. Instead of this oscillating curve that goes on and on forever, it's these repeating S-curves contained between vertical asymptotes that repeat forever and ever and ever, okay? Where they go from, again, if we want to call this one our starting curve or our starter curve, it's from -90 to +90, and really the only important point is 0, 0, and then we have a concave up half of a parabola to the right and a concave down half of a parabola to the left. So a couple things that we want to remember about the tangent curve, okay? For a tangent curve, for y equals tangent theta, the period, or the periodic length, is only pi radians. It's half the length of the sine curve and the cosine curve that have a period of 2 pi radians or 360 degrees. Okay? We also have, and this is the other new part, we have vertical asymptotes, all right? So asymptotes, spelled kind of weird, there's a silent P, kind of. And basically what we say is there is a vertical asymptote at every 90-degree interval. So think back to this in terms of radians. There are vertical line asymptotes, and the way that we write the equation of a vertical asymptote is we write it as a vertical linear equation. So x equals, that's how we write vertical lines equations. There is a vertical asymptote at every x equals 90-degree interval. But instead of writing 90 degrees, we write it as pi over 2. So it is pi over 2 n. Okay, so at pi over 2 at 90 degrees, there's a vertical asymptote. At pi over 2 times 2, all right, that would be, it's not every one, because it's not every 90 degrees, it's every 90 degree plus 180 degrees. So basically this is the way we write it. X equals pi over 2n, where n is an odd integer. Okay, so it's basically at 1 pi over 2. So 1 pi over 2 would be 90 degrees. At 3 pi over 2, that's 270 degrees. 5 pi over 2, that would be 450 degrees. And then likewise in the negative direction, negative 90, negative 270, negative 450. There are also vertical asymptotes, okay? All right, so the only other thing that I want to really specifically mention to you guys before we kind of wrap this thing up today, because I'm just kind of trying to lay out everything that's going to be asked of you when we eventually get to the point where we want to take a quiz. All right, they're going to ask you the familiar things, and we're going to look back at and kind of evaluate moving forward what these are going to look like. But you're going to be asked to identify periodic length, whether it's sine, cosine, tangent, cotangent, or eventually we'll get to cosecant and secant. You're going to be asked to identify periodic length. Everything else is going to work very similar, you guys. Okay, so we're going to be asked to identify phase shift in tangent. We're going to be asked to identify vertical shift and amplitude adjustments, which amplitude adjustment is just a stretch, a vertical stretch, right? All the same stuff that we've looked at the last several days for sine and cosine are going to have kind of a corresponding application to tangent and cotangent, all right? The only extra piece that they are going to at some point ask us for is they're going to ask us for domain and range values, okay? So they're going to ask us for domain and range values for, in some cases, sine and cosine, all that stuff. Basically, that's not a big deal. If we want to go back up here, we really could. I just want to check my camera, see if you guys can see this. If I want to fill in domain and range for the sine curve and the cosine curve. Remember, domain is just the x values. It's the width of these graphs. Well, it doesn't matter if you're talking about domain, or sine or cosine here. These curves continue on forever and ever to the right and to the left. So the domain for both of these would be all reals. Make sure you can see that. Yeah, you can see that, all reals. And the range is going to be the same for both of these as well. The range is the vertical limitations on this stuff, okay? So basically, both of these graphs, whether it's sine or cosine, oscillate between 1 and -1 vertically. So the range for both of these graphs, we would say our y values are between -1 and +1. Sorry, I know that's really squished in there. It's -1 less than or equal to y, less than or equal to 1. We're just listing or going off the graph to describe the width and the height limitations of these graphs. Well, these graphs never stop getting wider. They continue to oscillate forever and ever. And they never go above or below +and -1. So that's your range limitations. The other thing that you're going to be asked to do is kind of the same thing here for for a tangent graph. Well, you guys can all see that the tangent obviously does not have limitations vertically. Right? These curves go forever up and forever down, and there's forever many of them. So the range for the tangent graph is the part that's all reals. Right? Fix that. We say our range is all reals because these graphs these curves never stop going up and never stop going down. Now here's kind of the weird part. These graphs continue to repeat themselves forever and ever. So when you talk about your domain values or the width of your graph, you're going to make the same argument. You're going to say your graph gets forever wider to the right and to the left. So technically we almost want to say that our domain is all reals, just like we said for our range. Whoops, that's an R, not a D. Okay. Okay, but we have to remember the fact that there are these limitations. The range for each one of these periods, it goes to the right all the way up to 90 degrees and to the left all the way down to negative 90 degrees, but it never actually gets to 90 degrees, just like it never actually gets to 270 degrees. That's what an asymptote is. An asymptote is an invisible vertical line that the graph will approach but never get to or never reach. Okay? So we have to state that or stipulate that, right? And basically what it is it's just restating this asymptote portion right here. There is an asymptote at every pi over 2 multiple, or every multiple, or I should say every odd multiple of pi over 2 radians. So those are the x values that do not have a corresponding defined point. So we say our domain is all reals except the spots where there is a vertical asymptote. So we say for our domain, all reals except pi over 2n, and I'm just going to put a comma, n equals odd integer. Okay? Those are the only spots where our graph for this function is not defined horizontally, right? These graphs keep repeating, but even though they keep repeating, they're defined, there's always points in between every asymptote or every pair of asymptotes, but at the actual pairs or at the actual asymptotes themselves, the function's not defined because there is no corresponding point for those, okay? What we're going to look at tomorrow, you guys, in not nearly as many words, is I'm going to show you what the graph of the cotangent function looks like. And actually, I'm going to leave this in my legal pad here, and we're just going to pick right up below this, all right? Because I'm just showing you what I'd like you to have. So I'm going to show you what the cotangent graph looks like, as well as obviously the tangent graph, and then we'll get into some examples. The examples themselves, you really don't need to copy into your notes, but you're going to see that there's very similar carryover from the stuff that we've already done to the stuff that we're going to do for tangent and cotangent, and then obviously into secant and cosecant. All right, there's a lot of repetition with this stuff. It's a lot of kind of the same thing over and over again. You just have to get really comfortable with what does the parent portion look like. So the parent sine curve goes from 0 to 360, starts at 0, ends at 0. The parent cosine curve goes from 0 to 360, it starts at 1 and ends at 1. The parent tangent graph goes from negative 90 to positive 90, has asymptotes at those two spots, and then goes through 0, 0, and that's what we repeat to get our second and third and fourth or however many periods. Okay? So that's where I wanted to cut off today. I understand, you guys might have some questions or some lingering confusions or just maybe some uncertainty with this. That's okay. I wanted you guys to get this much copied into your notes today. We're going to copy a little bit more tomorrow. Then I'll show you a couple examples that you don't necessarily have to put in your notes, but will help you get ready to actually do the first worksheet that goes along with this stuff. All right, guys. I know some of you guys are stuck at home quarantined for a while. That's totally fine. Whether you're at home or you're at school, just shoot me your questions as they come up. Again, no assignment right now. Just kind of have these notes done. We'll pick back up tomorrow and you'll get the actual assignment tomorrow. Okay? All right, guys. Hope you guys are staying well. And take care. Have a good day. I'll talk to you later.